All right, everyone can see that? Excellent. So yes, I'm here today to talk about simplifying spatial data. It's a big part about what I do every day for work, so I do this a lot. And because of my work, which I'll describe a little in a moment, it is a pretty important factor of what I do as well. A small, slight micro confession. Originally, you might have remembered that this said simplifying spatial data in Python. And then I started writing a bunch of sample code. And then I looked at how long the code was. And as it turns out, writing a whole bunch of sample code and then putting it onto a slide is not the most exciting thing in the world. So instead, I've stuck to mostly GDAL command line commands. But when I do put the slides up, I will put the Python code up with it as well. Hopefully everyone gets what they want out of it, but that way everyone gets to go through this without just getting a wall of text in front of them, or at least as much of a wall of text as I've got. Simple, easy. So, rough outline, bit of housekeeping, some intro to me and to what I do, why this talk, where we're going to start, and then the actual process that we take to simplify data, basically to get it in front of customers in a useful and timely way. Okay? So yeah, a little bit of housekeeping. There is some code, Python, GDAL commands in Bash. I will make the deck available. But the really big thing that I wanted to highlight is that this does use the example of a real flood. This was the Brisbane flooding in 2011. For those of you that don't know about it, it displaced more than 130,000 people in Brisbane. It sadly cost 36 lives and caused at least, sort of in the sort of latest estimates, about $2.4 billion of damage. So please, if this isn't for you, please, I will try not to be too glib about it, and I will treat the data as just data. But if you do need to step out for whatever reason, please don't hesitate. Okay, so briefly, some introductions. As has been said, I've been doing this for a long time, much too long. I've been with geoscience. I've now been at FloodMap for 4 years. I've taught Python. I've taught spatial analysis in between. I've done all sorts of things. I've got a favorite map. I have a pet peeve in GIS, which I think everyone does as well, even if they don't admit it. And in my spare time, I'm a bit of a geek, a bit of a nerd as well. FloodMap, though, is the company where I'm currently working. It's a great place to work. Really wonderful people. Our mission is to build a better future. We work with agencies in Australia, the US, and for those who are New Zealand native, watch this space would be what I would say there as well. And our goal is to enhance public safety and to mitigate flood impact. So we're working with governments, whether it's state, local, federal, and we're working with critical infrastructure companies. We work with insurance companies. Honestly, we'll work with anyone. But we are working to provide flood information. Why do we do that? This is from the UN Disaster Recovery something, UNDRR. These are the annual, or the average annual losses in US dollars per country on flooding. Flooding is one of the most expensive disasters in the world. Average annual losses worldwide are about 390 billion US dollars. Okay, it's a very expensive issue, and we try and mitigate that issue. Okay, so what we deliver as an organization is stuff that looks a bit like this. Okay, so we deliver forecast, nowcast, and postcast data. Data that's before a flood, data that is at the time of the flood, and data that is after the flood for post-incident analysis. Okay, so forecast, where will it flood? What people, property, critical infrastructure is at risk. Nowcast, where it's flooding now. And postcast, where did it flood? Where are the damages? What facilities, what features have been impacted? Okay, and what that means is that we have a bunch of different data for different uses. Forecasts we use for flood preparedness, making sure that people aren't where the water is going to be. Nowcast we use for our response, so making sure that emergency services are on the ground when they need to be, in the places that they need to be, and doing things like closing roads so that people don't get stuck kind of seems obvious, but it's a difficult thing to do. And postcast, which is the bit after the flood. What happens when you have to go back and assess the damage, recover, and do the work of putting things back together. So because of this, we have different levels of data suitability. Data suitability basically is the idea that data is useful depending on how you're using it. Okay? We have a balancing of accuracy versus speed in an emergency situation. So it might be okay when we're looking at something like a forecast or a nowcast to have slightly less accurate data, as long as it's still useful or usable. While in a postcast situation, when we're doing post-incident analysis, we can have much more accurate data, where we can do those models, we can do that analysis, and it is still useful. Okay, so we've got a bunch of questions to answer. What's the data being used for? What scale? Are end users doing things like aggregating the data when they receive it further, or is the data usable as is? And of course, how do we deliver the data? Whether it's through things like OGC services, WMS, WFS, WCS, all those fun W acronyms, new OGC APIs, other APIs, or just giving people files. All of these things make a big difference to the way that your data has to be treated before you hand it over to someone. Okay, you can't email someone a 20 gigabyte TIFF. Okay, it'd be nice, but just not possible. Okay, and to be honest, if you could, they probably wouldn't like it very much. Alrighty, so why this talk? So yeah, we produce a lot of data. Okay, our customers can't see the data, we might as well not do anything. Okay, if we can't get it to people, why do we do it at all? And to be honest, it's the same with anyone working with spatial data. Okay, it's all well and good if it sits on your desktop, but if you can't show people, it's not particularly useful at all. And so we have things like issues with bad internet connections, memory-hungry applications, data that's just too detailed to make it useful, that make it harder to use. And so the aim of this talk is to take the data that we get out from our models and from our services and to simplify it, basically, to the point where it's still useful, but we can easily hand it over to our customers. Okay. So with a very simple starting point, okay, what we're going to be looking at are flood extents, which are where is water, how far does it go, and flood depths. Okay. When we at FloodMap produce our data, we start with flood depth. The flood depth is the model of how deep a flood water is at any given point. And a lot of the time, that's quite detailed because we have quite accurate data in particularly urban areas where people are most concerned about flooding. Okay? In rural areas, honestly, you don't often have data that's as accurate. It would be nice, but it's just not practical. And often, it sounds a bit naff, but it's often not as important because it's not affecting as many people and it's not affecting as much critical infrastructure or property. But we start with a digital elevation model, and it looks something like this. So this is Brisbane. So on the left-hand side, above me here, okay, this is a model of the 2011 Brisbane floods, at least along the Brisbane River catchment. Okay, so it's quite large, it's quite detailed, and we produce this on the left. That's a 1 to 1 mil scale. On the right, that's at 1 to 5K. So that's kind of building level scale. And it's the same data, it's just zoomed in. It's produced as a raster. It's at 1 meter resolution. Okay, so we chose 1 meter resolution because it's kind of a good balance for detailed analysis so that we can see, you know, how deep floodwaters are when they're affecting properties and assets. And it allows us to do very powerful analysis. But what that means is if you look at that raster file uncompressed, that is a 14.5 gigabyte raster file. Okay, that's a 14.5 gigabyte uncompressed GeoTIFF file. Even with compression, it's about 120 megabytes. Okay, so there's a lot of empty space, so it does compress very well. But even with compression, it's 120 megabytes, which genuinely makes it impractical if you're trying to deliver this in an emergency situation. Okay? For postcast analysis, 120 megabytes, fine, slap it on an FTP server, slap it in S3, hand it over, no stress. But for an emergency situation, you don't want fire manager, fire agency, police force, sitting there in their car on their phone trying to download that in a hurry on a spotting network. Okay, we need to be able to make this a bunch simpler. So we're going to start with simplifying raster data, and this is where the code comes in. So please don't stress about copying it all down. You're welcome to, but I will be putting these slides up later. I'm sure there is a place where FOSS4G allows for that. Okay, so first up, when you get raster data, first thing you want to do is look at the file compression. Okay, tools like GDAL allow you to very easily compress your raster data. Okay, and especially for something like a flood extent where we have lots of null data, compression can make a huge difference. I said before that it was a 14.5 gigabyte raster that compresses down to 120 megabytes. Okay, that's orders of magnitude small. Okay, we can do that really easily through the GDAL raster convert command. Okay, so for those of you that have used the GDAL command line before, this is the new equivalent of what was the GDAL translate command, is GDAL raster convert. You can still use GDAL translate, they both work. Okay, you can use lots of tools to do this, but GDAL raster convert takes an input, takes an output, and then you have these --co. This is a creation option, and depending on the output format of your raster, there's lots of different creation options, but if you have a look at the documentation for GeoTIFFs, one of those is the compress option. And so you can compress it as a JPEG or a PNG or a WebP file, or in our case, we're using the lurk deflate. Okay, so lurk is a compression format put out by Esri, limited error raster compression. By default, it is a lossless compression algorithm, as is the deflate compression. It works really well. It gets the data really small, and it's a really good place to start if you've got a data set with a bunch of null data. Okay. Alrighty. So this is kind of our starting point. From here, okay, we also want to think about how we're storing the data in the raster. Okay. So consider that your raster data is showing depth. You're probably showing that depth as, if you're in Australia and New Zealand, you're probably showing that in metric units, so meters. And if you're in the US, you might be showing that in feet and inches. Regardless, you're showing that as floating point information. So floating point pixels individually, 64-bit float, it's 8 bytes. Tiny individually, that's fine. As soon as you do that to every pixel, that's a very large raster. We've seen that already. Okay? But if you know a bit about your data, okay, I know that our flood depth raster is only actually accurate to the nearest centimeter. Okay? So at best, I have 2 decimal places of accuracy. Okay? Storing a 64-bit float, I think, I can never remember this number precisely, but I think 64-bit gives you something like 17 decimal places of accuracy. I don't need it. Okay? No one does. Let's be honest. Okay? So with a 64-bit float, if I change that to a smaller float, I can save a bunch of memory. But I can be a bit clever about it. Okay? This is accurate to the centimeter. Well, why can't I work in centimeters? Okay? If I multiply my data by 100, then I have whole centimeters. And that way, I can store my data as an integer. Okay? Whole number integer. The data's the same. Okay? The ratios are the same between the data. As long as I know that the data I'm producing is in centimeters, and I provide that metadata to my customers that it is in centimeters, then it's still very easy to work with. But it means that the size of the raster, okay, can go down substantially. Okay? So we can store that data as a 16-bit integer, or a 16-bit unsigned integer. That's fine. Depends on sort of what you want to do. I can actually probably even store it as an 8-bit integer if I wanted to. Okay? What that means is that if I'm storing a 16-bit integer, that's 1/4 the memory that's required for storing that floating point raster. Okay? So I can quarter the size of my raster just by doing a bit of maths and just changing the output data type. And again, it's very, very simple. Okay, we take the calculation, input, output. Okay, note here that we define A as the reference to a particular raster that we're going to perform a calculation on. Okay, so my A raster is my input raster, and then we perform the calculation 8 times 100 and set that to the output. Okay, There's a bit of a proviso. This only works in the very latest cutting edge version of GDAL because there's a, I know it's a bit dicey. It's because there's a small bug in there with propagating of null data values. In anything except the bleeding edge version of GDAL, you can use this instead. It's a bit longer. It's a bit less clear, I think, but it is very powerful. It's the new GDAL pipeline capability. And what the new GDAL pipeline capability does is it allows you to string together a bunch of different commands. In this case, the first part of this is doing the multiplication. Then we materialize it, which is basically do the calculation in memory. And then, as a third step, we set the data type. So we do that separately, and that way we don't lose data. It's just a bit of a weird one. Unfortunately, what happens under the hood is that currently data, when you have null data and you're converting to an integer, the data is rounded before you do your calculation, which is a pain. So you lose data that's kind of between the 0 and the 0.5 of your decimal place. Just those fun things that you have to learn when you do this the long way. But this does the same thing, okay? Soon this will be available to everyone and it's just usable everywhere like this. But for now, this works fine. Okay, it takes slightly longer, but it works fine. Okay, so that's our second step. Okay, we compress the data, we store the data as an integer. Okay, and then we go through the process of what's called downsampling. Okay, so this is the idea that you don't need 1 meter resolution raster everywhere. Okay, if you're looking to make a decision in a hurry about blocking a road, okay, 1 meter resolution is much more detailed, especially if you're looking at, well, to be honest, even suburb level, but particularly something like the level of a city. Rather, we can go a lot further and, for example, reduce our raster cell size from 1 meter to 10 meter by downsampling. And that's done through the GDAL raster resize command. Okay? We do that, it's very easy, and it gives you 100 times less pixels. So effectively, the memory that's required to store your raster drop off 2 zeros. Okay? So it's 100 times less memory required. Because again, we're trying to take this down to a size where we can easily give it to people. Okay? It's very easy to do with the resize command. We take a resolution. This is in projected units. Okay? So if your raster is in decimal degrees, good luck. But you would have to use decimal degrees instead. And this R is the resampling method. Okay, nearest neighbor is the fastest, but obviously you can do whatever resampling method works for you, whether it's like an average or whether it's a mode, you know, the most common values in the cells around you. All of these things work to resize the data. And so you get something like this. Okay, so on the left is the data at 1 meter. Okay, on the right is the same data with 10 meter resolution. Yes, at the level of a building, it's still pretty blocky, but there's enough detail there that you, as an emergency manager, can make a decision about how to respond to this flood event in a hurry and still be reasonably confident of the output. And remember that the data going into this is still a model anyway, so it's not like we're observing ground truthing every single piece of flood information at 100% real time ever. Can't do that. No one does that. So it's still a model to start with. So a slight bit of less accuracy, it's probably not a bad thing if there is another benefit to it. Okay? So this gives us a nice, easy raster. And at this point, this raster is about 2 or 3 megabytes. Okay? So we've gone from a 14.4 gigabyte raster to a 2 or 3 megabyte raster. And you could email this to someone happily if you needed to, and you're in a real hurry. Again, not the most useful, but you could do it. Okay? But we can go further. And we can go further by converting this into vector data. Okay? So, 5 minutes, thank you. So we can convert this to vector pretty easily. Okay? This is one of those fun ones where there's a lot going on with this sample of code. But the reason there's a lot going on is because converting it to a vector without cleaning up your data a little bit, okay, means that you end up with thousands upon thousands of polygons and you lose a bunch of, you actually gain a bunch of size because every vertex is more memory. So the first part of this is actually a raster pipeline, which is converting that data. And remember, because of that bug in GDAL, we have to do this over a few steps. This converts it into a simple footprint raster, where we're doing a calculation to say that everything that's above 0, anything where there is flood depth is 1, everything where there's no flood depth is 0. And we set the 0 to no data. And that just means that we have a simple presence or not presence of water. If you wanted to, you could threshold this however you wanted. Obviously, if you're not concerned about water that's 10 centimeters or less, you don't mind about a puddle, then that's your threshold. But in our case, it's very easy to threshold this. And so we can easily set the calculation, we set the no data, we materialize it, and then we can set the output type to byte, which is an even smaller data type. Okay? So a byte is 1/8 of a, 1 byte is 8 bits of data. Okay, it's about the smallest size of raster that we can create. We're only storing ones and zeros, we don't need anything else. Okay? And then we write it out and make sure that we compress the result, and it is tiny, under a megabyte. Okay? But from here, we can then use this raster polygonize command to take that footprint and then convert it to a vector output, our file or our flat GeoBuffer in this case, the polygonize command here. Okay, very simple. Okay, now there is a small note here. I won't spend too much time on this because I know that I'm running out of time. But you might also want to do some noise reduction first as well. Okay, so noise reduction, if you have that fun salt and pepper effect in your raster. A big example of this when we're dealing with flood data is swamps. So if a swamp is wet already, like on the ground, usually that's because there's presence of water there sometimes, and the ground sort of slightly shifts up and down, and when there's a bit more water, what you get is lots and lots of pixels, which don't really tell you anything. Okay, so often you want to do some noise reduction, and you might want to do that by filling holes. Okay, we can do that with interpolation. Again, very, very easy through the fill no data command, but watch out for your search radius, because the bigger the search radius, the slower this is. Or, more the point, we can do this with the sieve command, and the sieve command allows us to say, remove a block of contiguous data smaller than a particular size. So, you go from data that looks like this on the left to data that looks like this on the right as a vector polygon. So you sieve the data, turn that into a polygon, and we're nearly good to go. Okay? So this polygon looks okay. It is basically exactly the same extents as our raster data, but we can go further. We can simplify this as well. So first, check your projection. When you're simplifying a polygon data set, the units that you're using are projected units. If your data is in latitude and longitude, then obviously your projected units are going to be latitudes and longitudes, and all your tolerances are latitudes and longitudes. It's a pain. Project it to something more useful. GDA 2020 MGA zone 56. Nearly done. 30 seconds. So you can simplify this very easily. There's two methods to do that. Simplify, and I'll let you read the notes later. Simplify versus simplify coverage, and they use the Douglas-Peucker algorithm versus the Visvallingham-Wyatt algorithm. Basically, on the left, simplify, and on the right is simplify coverage. And the idea of simplify coverage is that it maintains the connection between adjacent polygons. And then finally, if you want to, you can reduce the vertex precision even further. And to do this requires a little bit more code because it requires some SQL. But you can shrink down how many vertex decimal places you're actually storing in a file as well. And if you have to give someone GeoJSON, it's a really good idea because you can shrink the file even further. Finally, to do that, SQL on the left, which is the actual command, the reduce precision command, and then on the right is the actual GDAL command that uses it. Okay? So our result is to go from 14.4 gigabytes to a 556 kilobyte flat GeoBuffer file. Okay? So this is a huge reduction. You can definitely give this to someone through an email if you wanted to, but most importantly, you can give it to someone in a hurry in an emergency situation. And basically the black on the outline there is the polygon. Inside that is the original 1 meter resolution raster. So you can actually see it's still pretty good. And if you're doing something like closing streets, hopefully, at least, this is all you need. And that's me. If you've got any questions, please shout out. Thank you very much.
Cool. Questions?
Just very quickly, but also you can transfer it, but I'm assuming that it will display much faster if you're putting it on a map
Massively
browser
so.
or something.
So if you stick that on a web map, you'll get a tiny file like that with a lower resolution up in seconds. If you stick the raster on a web map, well, okay, if the raster loads in your browser, it'll eventually display. If you try to just polygonize the raster's high resolution and then stick that into your browser, your memory will go up and your browser will close down. So yes, it might display, but it'll be real slow. So again, for display purposes, it'll be much faster as well.
Questions? Guess so, maybe. Questions? I got a question. One key thing you want to leave with them from your presentation?
Yeah, of course. Biggest key thing is understand how your data is being used at the other end. Okay? If someone needs the data in a hurry and they need to make a decision quickly, then talk to them. And with any luck, you can lower the precision and get them the data that much faster. That's me.
Great. Thank you, Henry.
Thanks so much, Carol.